Welcome back. In today's video, we're going to talk about tangent planes and using them to perform linear approximations for multidimensional functions. So we're going to kind of start by reaching back to Calc 1 a little bit. So if we recall the idea of a tangent line from Calc 1 of a function f of x at a point x naught, this is given by y equals f of x naught plus f prime at x naught times x minus x naught. And if we want to kind of draw a little picture, we can have like our, this is like our curve f of x, and suppose that this is the point x naught and then f at x naught. So I have a tangent line right here. We can actually kind of extend the same idea in 3 dimensions, and we get then from that the tangent plane as opposed to the tangent line. So now our function is in terms of x, y, and sometimes I'm going to use a z here to represent the value of the function f at x, y, just for notation to be cleaner. But this becomes we're going to wind up working with a tangent plane instead of a tangent line. So I can kind of try to draw a picture here. So this is kind of like our whatever surface it is we're working with, and we want something that's tangent to, say, the point right here. We'll call that x naught, y naught, and then f at x naught, y naught. We would just have a tangent plane there instead of a tangent line. That kind of indicates the tilt of the function there. And the equation that we wind up using for this is going to be z equals f x naught, y naught plus the partial derivative with respect to x at x naught, y naught times x minus x naught, and then plus the partial derivative with respect to y at x naught, y naught times y minus y naught. Okay. So there are a couple of observations that we can make. The first is that we note that this is the same idea as before. Only now we have 2 derivatives that we have to consider, each of the partial derivatives instead of just the one. So whereas in the original tangent line equation, we had f prime at x, x minus x naught. Now that we have 2 dimensions to consider, this turns into that f x x naught at y, or x f of x at x naught y naught times x minus x naught, and then that other piece with the other partial derivative f of y minus y naught, just like so. Okay, so this one piece has just been split into 2 because now we have 2 derivatives, but everything else is really just the exact same idea. And the other thing that I want to highlight is that this is also the same idea as the linearization of the function, which really just means that we can use it to approximate points nearby. And I want to note, though, that this can also be written with we substitute out that z for L of x, y, not z. Just to note that L is for linearization, and like I said, it can be used to approximate values of f of x, y, just as we did in Calc 1 with linearization or linear approximation in that class. So let's go ahead and get started with some examples. Our first example is going to be to find the tangent plane for f of xy equal to xy squared at the point -1, 3. So generally speaking, our equation for the tangent plane, like we said earlier, is going to be equal to z equals f at x naught, y naught, plus fx x naught, y naught times x minus x naught plus f y at x naught, y naught times y minus y naught. Okay, so if I plug in just like this information right here in for my x naught, y naught, because that's where we're interested in the tangent plane being at, we're going to get z has to be equal to f at -1, 3 plus fx at -1, 3, and then x minus -1, and then plus fy at -1, 3 times y minus 3. Okay, so now at this point, all I have to do is find my partial derivatives and then plug in the values we have. Oh, and we can kind of note that this guy right here, this is just -1 and then 3 squared, so that's just -9. So we'll hang on to that for later. All right, so now I guess we'll take our partial derivatives. F sub x of xy, just generally speaking, partial derivative with respect here is just going to give us y squared. And then partial derivative with respect to y is going to be 2xy. So if we plug in our numbers, we're going to get 9. And then for the other one, we get, it'd be 2 times -1 times 3. So that's going to give me -6 out of that one right there. All right. So now all we have to do is plug these numbers back in. And I'm not going to rewrite all of this, but we refer back to, I'll call it star. That's just this equation right here. So we're going to substitute all these values in here. We are going to get z is equal to -9 plus 9 times x plus 1, and then -6 times y minus 3. Okay, so this here is the equation for the tangent plane for the function given at the point -1, 3. If we want, we can kind of take a moment to look at what the linearization of that is, just so we can be a little bit more clear about what that looks like. It's really just the exact same idea as the tangent plane. The only difference is that we now call this L of xy instead of putting a z here. And this is equal to -9 plus 9 x plus 1 minus 6 times y minus 3. So that's pretty much all there would be to that. Let's do another example. We're going to find the tangent plane for f of xy equals y cubed e to the -x. And we're going to do this at the point 0, 2. Okay, so again, we start with the equation for the tangent plane, just generally speaking. And that is z equals f at x naught, y naught, plus f sub x, x naught, y naught, x minus x naught, and then plus f sub y, x naught, y naught, times y minus y naught, just like so. Okay, now I'm just going to go through and plug this guy in. Just to be clear, this is the x naught, y naught part of this equation. We're going to get z equals f at 0, 2, plus fx at 0, 2, and then x minus 0 there, and then plus fy at 0, 2, and then y minus 2. And then this piece here, f at 0, 2 is going to just be 8 times e to the 0, which is just 8. So we'll keep that in mind for later. And now we just have to compute our partial derivatives, plug in the values, and then substitute everything back into here. So my partial derivatives in general are taking the partial derivative with respect to x here, we're going to get negative y cubed e to the negative x. And then with respect to y, we're going to have 3y squared e to the negative x. And now I just have to plug in 0, 2. And I'm going to get negative 8 e to the 0, which is just negative 8. And then for fy, I'm going to get 3 times 4 times e to the 0, which is going to give me 12. And now I'm ready to take these values, plug them back up into this equation here, and that will give us z is equal to 8 minus 8, and then this simplifies, there it is, down to x, and then plus 12 times y minus 2. And that is my tangent plane. If we want to also look at the linearization of this as well, although, I mean, like, it's not asked for, but just so we're clear about what this looks like, that would be same equation, except we swap out that z for lxy, and then that's equal to 8 minus 8x plus 12 times y minus 2. And then that gives us linearization there as well. All right, so we can also talk about linear approximation using this. Again, kind of going back to the ideas in Calc 1. We have a linear approximation of f of x based at x naught. And we have that is approximately equal to, so if we have some value x, we can say that that's approximately equal to f at x naught plus f prime at x naught times x minus x naught. And really all this is doing is saying, okay, we have this curve, like so, and we have our base point x naught and a tangent line at x naught, which is really what this equation right here is just the equation for this whole tangent line. And what we're really curious about, though, is maybe the value of f at this point right here, x, okay? Well, what we note, though, is that this point that's up here on the tangent line, I don't know, we can call it y if we want to. This is pretty close to what we're actually looking for, right? So this is f(x), f of x. These two are pretty close, but this right here on the tangent line is way easier to compute maybe than what is actually on the value here. So then we're able to approximate this based off of the tangent line. And we have the same idea, again, in 3D, except this time, instead of using the tangent line to do the approximation, we will use the tangent vector. So we can approximate a function f at xy using the tangent plane based at a nearby point say x naught, y naught. And just as this equation here uses the same equation from the tangent line, this approximation is going to use the same equation as the tangent plane. So f at xy is approximately equal to f at x naught, y naught, plus the partial derivative with respect to x at x naught, y naught, times x minus x naught, and then plus f sub y at x naught, y naught, times y minus y naught. So again, this is the same equation as the tangent plane. Let's work an example. In this example, we're going to approximate f xy equal to xy squared near the, or at the point negative 0.95, 3.01. So as always, I like to start out by writing out the equation that we're going to be using. So we're going to use the equation fxy is approximately equal to f at x naught, y naught, plus partial derivative with respect to x at x naught, y naught, times x minus x naught, and then plus the partial derivative with respect to y at x naught, y naught, times y minus y naught. And in order to be able to fill out this equation, xy, that's just going to be the point that we're going for right here. But this x naught, y naught is just a nearby point to this one right here, that maybe it's considerably easier to compute this value at xy squared as opposed to this right here. And we note that negative 0.95 and 3.01 is pretty close to negative 1, 3. Okay. So this guy right here is going to be our x naught, y naught. And this piece right here is the xy. So all we do is take these two and then plug them into this equation here. So f at negative 0.95, 3.01 is approximately equal to f at negative 1, 3 plus the partial derivative with respect to x at negative 1, 3 times x negative 0.95, and then that's going to be a plus 1 from this guy right here because we'll have two negatives, and then plus f sub y at negative 1, 3 times our y, which is 3.01, minus y naught, which is 3. And we've actually already worked with something that was really similar to this before. We found the equation for the tangent plane using this point. So we know that we already have that f at xy, generally speaking, is approximately equal to negative 9 plus 9 times x plus 1 minus 6 times y minus 3. And again, this is the equation from the tangent plane from earlier. So really all I have to do is, we don't even have to go through all these steps of getting f sub x and f sub y again. We just have to substitute in the xy that we're given to work with. So f at negative 0.95, 3.01 is approximately equal to negative 9 plus 9 times, and then our x is now negative 0.95 plus 1, and then minus 6 times y, which is 3.01 in this case, minus 3. And at this point, all you got to do is throw all of this into your calculator, and that's going to give you negative 8.61 as the approximate value for this right here. Or, you know, plugging in negative 9.5 or negative 0.95 in for x, and then 3.01 for y there. Let's do one more example. In this one, we are going to approximate f of xy equal to y cubed e to the negative x at the point 0.01, 1.95. Okay, so again, generally speaking, f at xy is approximately equal to f at x naught y naught plus f sub x at x naught y naught times x minus x naught plus f sub y at x naught y naught times y minus y naught. And in order to be able to fill this out, we already have, this is the xy, but we still need our base point x naught y naught. And 0.01, 1.95 is approximately equal to, well, this is really close to 0, and this is really close to 2. And if we go back and look up at this equation here, 0 is way easier to plug into an exponential function than 0.01, so we've made a really good choice there, and then 2 cubed is pretty straightforward as well. So this means then that this is going to be your x naught y naught, and like we said, this is xy. So this equation here then becomes f at 0.01, 1.95 is approximately equal to f at x naught y naught, which is this 0.2, so f at 0.2, plus f sub x at 0.2 times x, which is 0.01, and then minus 0 there, and then we have plus f sub y at 0.2 times 2 minus 1.95 is what's going to go in for this piece right here. Well, once again, we've actually already found like the tangent plane for this equation here at the point that we've chosen. So once again, we can kind of reuse that information, and we have that f at xy is approximately equal to 8 minus 8x plus 12 times y minus 2. So again, this is tangent plane equation from before, based at this same point for the same equation. So all we have to do then is plug in the x and the y that we've been given. So f at 0.01, 1.95 is approximately equal to 8 minus 8 times 0.01, and then plus 12 times 1.95 minus 2. And throw all that into your calculator, and you're going to get 7.32. So the value of this function here at 0.01, 1.95 is approximately equal to 7.32. So anyway, a lot of this really looks quite similar, and the big idea here is that this same equation, or at least this portion of it, just gets relabeled and reused over and over again, in the same way that when we worked with the tangent line in Calc 1 to approximate values of the function, that all of that works out just kind of reusing the same phrase, or the same equation, all those same pieces. So hopefully this was helpful, and that's really pretty much it for this video.